Thank you to Hearts to Humanity Eternal for allowing me to give this research presentation on a high-performance neuroprosthesis for speech decoding and avatar control. This is a new study that was just published in Nature. And I just want to acknowledge the H2H8 support. They've supported us through two research projects. One is a spelling device, which I'll talk about today. And I was a 2022 EECS Explorer and Guardian, and as well as the second paper, a high-performance speech neuroprosthesis, which will be the main topic of today's talk, which I was a co-first author, and also a co-author, Peter Wu, was also an EECS Explorer. So a brain-computer interface that could decode intended speech from brain activity could potentially help persons who have severe paralysis. And how this would work is that a human user would have electrical activity in their brain, and then we can use a neural interface, for example, a microelectrode array or an ECOG array, to record that brain activity. And then we can convert, using this device, those brain activity signals into digital signals, which then get sent to a data processing machine, and which can be decoded into speech, text, or text, for example. And we validated this approach with able speakers, people that can speak. And this was the work of my advisor, Dr. Gopala Anumachipalli, who showed that from brain activity, we can directly synthesize audible speech. And also, Joey Mackin showed that you can use brain activity to decode text as well. So these were early approaches that showed that it was possible with people who did not have paralysis. So this and many other works inspired us to start the Bravo clinical trial, BCI restoration of arm and voice. And this is a clinical trial for long-term communication and movement restoration to people who have severe paralysis. So this was our first participant, Pancho. You can see here he's using, this is the device he normally uses to communicate. So he slowly presses the letters with a stick attached to his baseball cap. And you can see that this would be extraordinarily slow, especially if you have paralysis. It's actually very difficult even to move small movements. So our initial speech PCI, and this was just before I joined the lab, showed that we can use this device called ECOG, electrocorticography, implanted over the surface of the part of the brain that corresponds to speech. And we can record these signals and use them to decode text. So there, we kind of employed this real-time signal processing pipeline to decode an AI to decode the text. And one thing that we saw is that essentially we have performance that's with and without a language model. So a language model similar to ChatGPT or other language models, they basically learn the structure of speech. So for instance, the word I am is more probable, or sorry, the phrase I am is more probable than I cool. And a language model can sort of auto-correct the outputs of the decoder. So without the language model, we're at about 60% word error rate, but we can drop that down to around 24% word error rate. And we can get pretty reasonable decoding speeds, around 15 words per minute. And one thing that I kind of glossed over is that how this works is it's classifying individual words from a very limited vocabulary, so about 50 words total. And then after getting the probabilities of each word, a language model is then applied to find out what is the most likely sequence of words. And the output of that is then decoded. For instance, I am very good. So let me show you an example. That's the prompt. And then the participant attempts to speak, and you can see the decoded output in real time from the participant's brain activity. So this was extremely promising because although it's still a 50-word vocabulary, this was the first demonstration of decoding speech in someone who has who is completely paralyzed and has no ability to speak. And this kind of inspired us to try to move beyond this. And this was the paper which I'm fortunate to be a part of, called a spelling BCI, or sorry, that attempts to do a spelling BCI, which essentially is similar, but instead of classifying individual words, the brain computer interface classifies individual letters and the participant tries to spell out the words. So instead of I am very good saying I am very good, you would spell out, or the participant would spell out those words, and they would use what's called a NATO code word. So for instance, Alpha, Bravo, Charlie, those are code words that correspond to like A, B, or C. And those were the words that Poncho would attempt to speak. And then the brain, and then similar to before, a neural network would classify the word. And we can see that we get this diagonal matrix essentially says that it's highly accurate. Um, it's about 60% accurate on the words themselves, but as you use a language model to kind of autocorrect the sentence, we can get pretty low character error rates, as low as 6 to 8% character error rates in real time, which is this result shown right here. And this chart essentially shows as you apply a language model, like for instance, if you just use the neural activity, you get a higher character error rate than if you were to use the language model as well. So here's an example of here. So what this allows Poncho to do is use a large vocabulary, not just 50 words, but can say over 1,000 words, and essentially it's unrestricted vocabulary. So you can see she tries to say, or he tries to mime the letters one by one. And this system is a bit slow, so I'll speed it up. And the updates that you're seeing is the language model kind of auto-correcting what he's saying. So he attempts to spell out that as all right. So with these exciting proof of principles and milestones in the field, we sort of wanted to look to see how can we expand beyond just single letters at a time or like a restricted vocabulary. And for this, we worked with our newest participant, Anne. Anne had a stroke when she was about 30 years old, and she was playing volleyball with some friends and ended up in the hospital. And this left her with no ability to communicate, no ability to speak. And she reached out and enrolled in our clinical trial as a new participant. And the main difference between her and B3 in terms of the device is this device has double the amount of electrodes. So the grid itself is slightly larger, but the main difference is the amount of electrodes or the density of the electrodes. And one thing we saw immediately that we didn't see, so keep in mind, for B1, the NATO spelling code word classification was about 50% accuracy. We immediately saw almost high performance decoding within days, or actually, within days to weeks of training. We saw almost 100% accuracy. And what you can see here, classifier frozen, is we froze the classifier, meaning the participant was training all the way up into here, but even without retraining, she could days afterwards still get high performance decoding. So almost 80 days after training the model, it still works using her neural activity. So this shows that this device is stable over time. It's not something that will just that you will need constant updating for it to work.
What is NATO?
Oh yes, I should have explained. So NATO is stands for North American Treaty Organization.
North Atlantic.
Or sorry, North Atlantic. Yeah, that's right. Yeah, apologize. But anyways, it's the main point is that it's a code words for the alphabet. So it's used in like radio communications, like for instance, like Alpha, Bravo, Charlie, Delta, and
Uh,
those correspond to like the letters that you would attempt to mime. And another thing we saw almost immediately with Anne was persistent somatotopy. So what this means is that the parts of her mouth that would normally function if she didn't have a brain stem injury, that those movements are actually encoded in her brain. So, for example, these red electrodes kind of code for vocalization, and the blue electrodes code for tongue movement, and the orange codes for lip movement, and the light yellow corresponds to hand movement. So this kind of shows that distinct areas of that grid encode different movements of her mouth. And this is basically the basis of this new project. So introducing our most recent work, high performance BCI for speech decoding and avatar control, we tried to essentially decode three outputs at once because we've shown we could decode text, but we also wanted to see if we could directly synthesize speech as well as directly animate a live action avatar. And just for clarity, we tested three different training sets. So one is the 1024 word general. So this is over 1,000 English words. These are the sentences that we tested with our participant. And this set covers about 85% of the English language. And we always tested on unseen sentences. So not repeats over and over again of a single sentence, but new sentences that she's never said before. We also tried 529 AAC. So this is about a closed set of 529 phrases relevant for daily life. And then we tried an even more restricted subset of 50 phrases. So long story short, this is basically to test like the effect of the vocabulary size on performance. So in our first demonstration, we showed that essentially we could get high performance text decoding, and this is using what's called CTC loss to optimize. So this is commonly used in ASR. So anything you would like, if you use Siri or Alexa, this model is actually quite similar to that. So how it works is the neural activity is passed through a bidirectional recurrent neural network. And at every time point of the neural activity, the model tries to predict which phoneme is at that time point. And then it gets all the probabilities of the different phonemes. Phonemes are the units that kind of make up speech. And then a beam search algorithm is used to find the most likely sequence of phonemes based on the neural outputs. So then after we get the sequence of phonemes, we then use language modeling to convert that sequence into the actual word themselves, or sorry, the words and ultimately the sentence. So what we saw was that the word error rates go as low as 25 or median 25% word error rate. So, but this is different from previous studies because this is much higher vocabulary and directly decoding speech. And then we also saw the phoneme error rates were about 28% with the just from neural decoding, but we can get those much lower with after applying the language model. But perhaps most importantly is the decoding speed on the very right, which before we were, so this dashed line represents the speed of her current device that she uses. And previous BCIs were around this range towards the bottom quartile. But this BCI actually gets all the way to 78 words per minute. So it's much faster than previous devices, which is important for effective communication.
mhm.
And another thing that we saw is that the error rates decreased over time um, as you collected training data. And we could get good performance within 2 weeks of training. So the actual amount of neural data that went into the model was about 17 hours, but with the participant, we actually only collected for about 2 weeks to get good performance. And the vocabulary size that we used was about 1,024 words, but we did an ablation that showed that as you increase the vocabulary constraints, the size of the vocabulary, that it generalizes to over 30,000 word vocabulary. And these are some example sentences just to get a gist. For example, 0% word error rate would be perfect, but the median, which is 25%. So the median was kind of like this. So for example, the target, you have no right to keep us here. The decoded sentence would be something like, you have no right to be out here. So let me show a demonstration video. And here the participant, she's going to see a prompt and then she's going to silently attempt to mime the words on the screen. And after she's done, the AI will basically decode that neural activity into the written language using the method just discussed. I'll let this run for a few trials. Some of the sentences are a little odd, but they make it in there. Right. So, so this was the text decoding, but we were not just interested in decoding the text, but also something that matters a lot is speech, because speech there's a lot of information that is communicable with speech. For example, like the emotion, the pitch, how that you're feeling, a lot of nonverbal communications that are important to feel embodied. So the modeling technique that we used here to synthesize speech directly was actually quite similar, but instead of predicting phonemes, we predicted discrete speech units. So you can think of these as we use a self-supervised learning model to take a target waveform and convert that into discrete speech units. So we predicted those discrete speech units, and then we use a speech synthesizer, which is essentially this entire pipeline on the right, to then take those acoustic units and transform them into speech. And another thing we did is we found a clip of her that she gave to us with her permission of her during her wedding video. And we were actually able to use that clip to restore her voice, not just some random text-to-speech voice, but how she would have sounded if she did not have paralysis. And these are some example spectrograms. So on the top, you can see the decoded speech. In the middle, I think you are wonderful. And then on the bottom, the reference speech. And you can see that they are quite similar. I'm going to skip over this MCD for now. So one thing we saw is that so for the 1,024 word general set, it's about 54% word error rate, which is that is worse than the text. But as we go to smaller vocabulary, for instance, 500 phrases or 50 phrases, the accuracy increases. And one difference here is that these are human transcribed accuracies. So they're not just like ASR or what we think, like some statistics of what the speech sounds like. These are what actual humans wrote down, what they said, what they heard, and we compared what a bunch of untrained human listeners heard compared to what the text transcript should have been. And that's how we kind of got these word error rates and character error rates. And lastly, we wanted to try something a little bit new, which was to see if we could directly decode a facial or gestures, oral facial gestures, and use that to drive an avatar. So for this, we partnered with a company, Speech Graphics, who helps to make speech to avatar animation software. And they created a muscle animation system. So you can think of this as the muscle of an avatar, and they created a way to map speech to those muscle movements and use those muscle movements to animate the avatar.
Hmm.
What we did was we took the neural activity and then we essentially predicted those muscle movements. So for example, I think you're wonderful. There's a sequence of muscle movements, which are here in the center, that correspond to that sound, I think you are wonderful, or in this case, great to see you again. And we predict those muscle movements, which then drive the avatar. And one thing we did was we wanted to look at the accuracy of um, the actual animations themselves. So the avatar is a bit different. Even professional lip readers are not very accurate at lip reading. So we did binary perceptual accuracy instead. So we basically asked listeners or watchers in this case, look at look at this video and tell me out of these two phrases, which one does it look like it's corresponding to? And we can see we can get well above chance accuracy doing that. And then another thing we tried was to see how well the avatar's facial movements correlated with those of somebody who is an able-bodied speaker. And we could see that if we this in the blue, an avatar person correlation essentially shows that for jaw, lips, and mouth width, like basically the avatar's movements correlate well with how an able speaker would have moved.
Hmm.
And the last thing we wanted to try is essentially to see if we could use the avatar to directly express emotion. So for this, we had our participant and try to make various expressions. For example, lips back, pucker lips, closed mouth, open mouth, lower tongue, raised tongue, as well as make a surprise face, happy face, or sad face at 3 different intensities, high, medium, or low. And we saw that we could get pretty good classification accuracy, actually up to 96% for just between surprise, happy, and sad. And we showed in a demonstration video that we can decode these classes and use those to animate the avatar. So it's a bit slow, but we're working on getting the latencies down, and we think that we can get this to be a much faster system. And let me allow one more gesture to play. So kind of that was the full system in a nutshell. But one thing that we wanted to try is it's great that we can decode these modalities independently, but what if we could decode the avatar, the text, and the speech simultaneous? Because when we speak, our face is moving in tandem with the speech.
Mm-hmm.
And in addition to that, the text information is also important to convey what's being decoded as well. So for this, we created a multimodal demo that decodes the text to speech in the avatar simultaneously and in her own voice.
I think you are wonderful. Give me a few minutes.
I think there's a few more examples.
What do you think of my artificial voice?
And you can see her mouth moving slightly, but it's actually just residual articulation. It's not intelligible or decodable.
Mm.
What have you been doing?
So in summary, this was a demonstration of rapid and high performance text decoding, intelligible and personalized speech synthesis with someone who can't speak, and the first demonstration of doing a real-time avatar control and from a person's brain. And really important for clinical reasons, we could achieve stable performance within a few weeks of training models. So it's great if these above 3 points can be decoded. That's nice as a demonstration, but having something that's stable and high performance that does not need retraining immediately after each session is something that's really important.
Mhm. So this the objective is to be able to get this working, and all the patient need is to have when you have something attached to the brain, it's on the outside of the skull, right?
Right. So basically, there's a pedestal that sits on top of her skull, and then this is the digital head stage,
Mm,
which then these signals are streamed here into
mm.
the pedestal, into the head stage, and then into the computer. But we are working on a version that is wireless.
Oh, okay.
So that's really important because we would want to have the person always need to be plugged into no matter what.
And then the rest will fit into kind of a small computer with a screen with the avatar.
Right. Yeah, that's actually the second thing we're also working on is making the computer miniaturized. So she uses the same machine as Poncho, which is it's a very large computer. It's
Oh, okay.
a rig. It's huge.
It's a,
About three
it's,
by
it's
four.
a rack.
And yeah, it's well over 100 pounds. And it's important for that to be miniaturized. So it could be on the computer with the avatar, or another device.
Yeah, so you need Peter Wu is in ECS, right? So he's doing some of the electronics, or
Yeah. So Peter actually trained the part that goes from, so in the speech synthesizer, um, Peter trained the part of the model that goes from the units to the speech for her own voice.
uh,
So he basically, I created an original implementation, but he created a much faster version.
mm,
That's what was shown in the main demonstration videos.
uh,
Is that what people call tokenizing the signals? Kind of. Oh, anyway, I have a question about the matrix of electrodes. Is it, you guys know ahead of time where the zones are, or is it something that you found out as part of this experiment?
Right. So we use an fMRI to basically localize where we think the speech regions are. So um, and would go into an fMRI machine and then attempt to speak and perform various tasks. And we can use that to localize the area that we believe would it contain those signals, and only then, after we've identified that region, go through the proper process to start the neurosurgery.
Okay, good.
So if you don't need the screen and you just have some kind of speaker, then somebody, if you miniaturize the computer, you can actually have somebody carry the whole thing, walking around, talking from the brain to the speaker.
Like, oh, I see. So to recapitulate, if you didn't need the screen, you could just have like a speaker.
Yes.
Right. So we envision that basically that would be, so all these outputs are up to the user's preference. We kind of view it as, most people, I'm assuming, would probably prefer to have speech because, well, actually, we've seen this, that in various literature review studies that participant like feedback studies, that participants who have paralysis do want to restore the speech, the actual sound, and that's very important. But the avatar is kind of like an optional modality. It's something that's not required by any means, but it's only optional. For example, our participant expressed to us, and she felt that she could use the avatar to be a counselor, perhaps counsel other people in similar situations.
That's ambitious.
Well, that means with the avatar, she doesn't have to be there, right? So your avatar can be projected to somebody's screen.
Right, exactly. And we
That's
kind of,
true.
Yeah.
that's right.
They can be on Zoom.
Yeah, assumes, yeah, avatar.
So in your estimation, you make a lot of progress. You think this can maybe in a few years become a real sellable device for patients, or?
Yeah, that's a great question. I definitely feel within, it's not going to be 40 years or 50 years. I think it's going to be within the next 5 to 10 years.
Oh, okay. Well, within your lifetime. Within
Because,
our lifetime too.
well, like for example, if we go to let me see if I can find it. The performance with the code words, the NATO code words. So here we already see near 100% accuracies. And with a language model, presumably those accuracies would be even higher.
Mhm.
But this is already near performance needed to actually be like usable. We
Yeah.
just need to get the speech word error rates down.
Hey, Kaylo. So what you have been working is with a language that is alphabetic words. So in the case of a language such as Chinese, which are character-based, would it make your job easier or make it more complicated?
So that's a great question. And we feel that the speech synthesis and the avatar part is language agnostic. So with the speech synthesis, these are just representing the sounds. So
Yes.
any language can be used, and it shouldn't be more difficult whether you use, if it's Chinese or even low resource languages, many languages and dialects that have less or not as many speakers. So for the speech synthesis and avatar, we think that this can work for many languages. For the text, there is some consideration depending on how the language is actually written. But at the end of the day, all languages, they're comprised of a set of phonemes that there's only so many sounds the human vocal tract can make. But it is the ability to go from those phonemes to the language. It depends a lot on the modeling tools available for that language at this stage.
So I want to add to that because, there are quite a few projects out there, and one of them is under the auspices of AI for Good, that people are creating systems to preserve lost languages. or near lost languages from certain cultural groups that are facing not too many young people trying to learn the language, so they're trying to preserve it. So this could be one way that they can do that.
Yes, in the sense. So actually, this kind of reminds me of so my advisor as well as other groups are looking at low resource language because a lot of these languages that are dying, they don't even have like written alphabets or letters. So that's one topic of interest in our lab and others is understanding how can we represent that language in terms of just the speech from the speech itself, because they need translation tools as well, even if it's
Yes.
yeah. So
I think one of the interesting language that is under a lot of scrutiny is the so-called Maori language spoken by the New Zealand natives. And that language is pretty much on the verge of dying. So a lot of work's being done in that language too. So, yeah.
Oh, wow. Yeah, that's great.
Okay, with your, very successful research and publication, you're about to graduate?
Not quite. I'm doing my master's thesis.
Okay.
I also need to, before I forget, there's one more slide. I wanted to make sure I acknowledge everyone on the team. So basically our great participants, their caregivers and families, the speech graphics team, the support staff, funding sources, and the Ganguly Lab, and everyone that was involved, because Sean Metzger, Margaret, myself, Alex, were co-first authors, and then Gopala and Karen Nash also helped, but Eddie Chang was like the main leader.